Okay, what if you could zoom in on a single living cell, create a perfect 3D map of its surface, and at the exact same time, figure out what every single molecule on that surface is? I mean, that's been a huge goal in science for, well, forever. Today, we're going to talk about a brand new technique that finally gets us there by creating a tiny nanoscale superteam. Let's get into it. So, here's the big problem, right? Imagine trying to get a super detailed 3D picture of something incredibly fragile, like the surface of a living cell. It's soft, it's squishy, it's floating around in liquid. Now, on top of that, try to figure out what it's made of, molecule by molecule, without destroying it. It's like trying to read Braille with a hammer. You just smash everything. What you really need is a tool that can see with its fingertips, but without ever actually touching. All right, let's meet the first member of our super team. This is the ultimate mapper. Its call sign, SICM. So what is SICM? It stands for Scanning Ion-Conductance Microscopy, and it's just a brilliant solution to that whole don't touch problem. It uses this impossibly small glass tube called a nanopipette as its eyes. This little pipette measures the flow of ions in the liquid around the cell. As the tip gets closer to the surface, that gap gets smaller, and fewer ions can squeeze through. By keeping that ion flow constant, the microscope knows exactly how far it is from the surface, building this amazing 3D map without ever physically bumping into it. And wow, just look at what it can do. Think of it like a record player, but one from the future that can read all the music from the grooves without the needle ever touching the vinyl. Zero contact means zero damage. And that lets CCM map really soft, delicate things with insane precision. I mean, look at this spiral made from a soft polymer. You can see every single sharp edge, every corner, all perfectly mapped out. Okay, but here's the thing. SICM gives us this absolutely beautiful map. We know the where. We can see all the mountains and valleys on the landscape of a cell. But we're still missing the what. Is that little bump we're seeing a protein? Is it a piece of a virus trying to get in? The map alone just can't tell us. For that, we're going to need our second hero. So let's bring in the team's chemical specialist, the identifier. Meet TERS. TERS, that's Tip-Enhanced Raman Spectroscopy. And its superpower, it's basically a chemical sniffer on a nanoscale. Here's how it works. You shoot a laser at a tiny metal-coated tip. This creates this massively amplified light signal right at the very point of the tip. When that super bright spot hits a molecule, it makes the molecule vibrate and scatter light back in a really specific way. And here's the magic. Every molecule has its own unique way of scattering light, its own chemical fingerprint. TERS reads that fingerprint and tells you exactly what you're looking at. And this isn't just some cool party trick. This is a true game changer. Hey, don't just take my word for it. This paper from Analytical Chemistry says that TERS gives us unprecedented spatial resolution. We are talking about seeing chemical details that are way smaller than the wavelength of light itself. For a long, long time, physicists thought that was just flat out impossible.
So you've got SICM, the ultimate gentle mapper, and you've got TERS, the ultimate molecular identifier. What do you think happens when you put these two powerhouses together on the same team?
Well, you get a perfect partnership, a single revolutionary instrument called SIC-TERS. And here's the setup. It's so elegant. They use the exact same nanopipette probe for both jobs. As it's hovering over the surface, it's using that ion current to build the 3D map. That's the SICM part, doing its thing. But at the exact same time, a laser is aimed right at the metallic tip of that probe, which then reads the chemical fingerprint of whatever is directly underneath it. That's the TRS part. They are mapping and identifying all in one go. I love this because it shows you the journey from a simple, brilliant idea to the complex reality of making it work. On the left, you've got the clean, simple concept. And on the right, that's the real deal. A beast of a machine built around a high-powered microscope sitting inside a special box to keep out any tiny vibrations or electrical noise. Now, the absolute heart of this whole thing, the piece that makes this entire partnership possible, is the probe itself. It's not just any old pipette. It's a custom-built plasmonic nanopipette. All plasmonic means is that it's coated with a special metal that can grab onto light and concentrate it, creating that super enhanced signal we need for TERS. So how do you even make one of these? Well, first, they take a tiny glass tube and use a CO2 laser to heat it up and pull it apart, which creates two incredibly sharp tips. Then, inside a vacuum, they sputter it with a super thin layer of gold or silver. And when I say thin, I mean it. The research shows about 10 nanometers is the sweet spot. That thin metal coating is what gives the probe its superpower.
Okay, so the machine is built, the super probe is locked and loaded. How does it actually perform? Let's put it through the ultimate nanoscale test.
Now, to really appreciate what you're about to see, you have to get this one key difference. A normal laser measurement gives you what's called a far field view. The signal is blurry, it's indistinct, it's like trying to hear a single violin while the entire orchestra is playing. But the TEERS probe, it creates a tiny near-field hotspot. It lets you lean in and listen to just that one violin, perfectly clear. And this graph is the money shot. It tells the whole story. Look at that bottom line, the far field. That's the weak, mushy signal you get when the probe is far away. But as the tip gets closer, you enter the near field, and boom, the chemical signal just explodes with detail. But it gets even crazier. As the probe gets so close it gently presses on the surface, the signal changes again. It's showing deformation. It is so sensitive it can literally detect the stress on the bonds between atoms. That's just mind-blowing. So just how big of a difference are we talking about here? The signal enhancement factor is calculated to be around 10 to the 5th power. That's a signal boost of 100,000 times over. It is literally the difference between hearing a whisper from across a room and standing next to the speakers at a rock concert.
So why does all this matter? What's the bottom line? It means we can finally truly see and identify on the nanoscale at the same time. We can do it gently, without destroying the fragile living things we want to study. The sensitivity is so off the charts, we can even see the physical stress a tiny probe puts on a surface. And this just blows the doors wide open for new research in biology, in chemistry, in material science, everything.
So we've built this incredible new microscope, a tool that can draw a perfect map of a living world, and at the same time, ask every single citizen in that world who they are and what they're doing. So the only real question left is, now that we can finally ask, what secrets are our cells finally going to tell us?